Hey folks, all right, here we got a third example for motional EMF. Now, if you need to, go ahead and pause the video and copy all this stuff down. All right, now you'll notice the picture is a little different from the previous example. It's similar, but there's some differences. We've got a battery in the circuit now. I put a resistor in there that represents R, the resistance of everything in the circuit, okay? And then for reference here, I rewrote basically the answers to our work from the previous example. There's two slight differences I want you to note, and there's a reason why I'm doing this. I moved the dV when we were doing the work, and we got the V without a coefficient in front of it. I moved the term with the dV dt to the same side, so everything equals 0. Okay, so that's our first issue, or first slight change. And the second change is in the exponential term here for our actual answer. This was negative b squared L squared over Rm times T. I wrote all the constant down here, and I had to flip it over because I'm putting it in the denominator, okay? Now, there's two things I'm going to show you this example. The first is a math trick, okay, a math shortcut. You might notice already that whatever is in your constant term, whatever that doesn't have a variable with it, that's the leading coefficient in your answer, okay? Now, by the way, this shortcut only works for a first order differential equation that has a constant like this out front, okay? But that constant is your coefficient out here. And you'll notice whatever's in front of the dV dt, okay, that is the exact same thing that's in your exponential term in the denominator, okay? That's kind of like the time constant for your, in this case, velocity, okay? So it kind of functions the same way, just like an RC circuit has a time constant. This velocity has a time constant as well. Now, for the most part, I would imagine if you end up taking the AP exam, College Board would be just fine if you got to this step and then wrote the answer out. I think they'd be fine. I don't think they necessarily need to see calculus unless they specifically ask for it. So I just wanted to mention, and the rest of the first order differential equations that we have, I'm not going to go through all that crazy math. We're just going to go from this line of work to the final solution, okay, using these shortcuts. Okay, so that's the first point I wanted to make in this example. Now the second point is the F naught, okay? So F naught is different depending on what is pulling the circuit or pulling the bar, okay? So in this case, this is a kind of a nutty little case here, because here's the deal. You got a battery in the circuit with the voltage V. Now, by the way, this is voltage. The V in our equations for reference here, those are velocity, and I'm sorry they look very similar, but just an FYI, this is velocity, and over here, that's voltage, okay? So the battery's got a voltage. So the battery is going to drive current. Well, again, we're pretending it's positive current that way. And I'm going to call that I1, okay? And that current would be just V over R, okay? And that current, which I'll draw here as well in the bar itself, is going up. That current's going to experience a force. And if you do your right-hand rule, so you would face your hand up the page along with that current, you would curl your fingers into the page and your thumb points left. I will call that F1, okay? That force is constant, and that force, F1, would be I1 LB, okay? So in your equation for motion, that would be your F naught, okay? That's a constant force that's pulling the bar to the left, okay? But as the bar moves left, you get the motional EMF. And you get, from the previous examples, you start to get a current that flows down and around the circuit. I'm going to call that I2, okay? And that current feels a resistive force to the right. I'll call that F2, okay? And so that force will build, okay, until force 2 equals force 1. And when that's achieved, the bar will reach a terminal velocity. It will stop accelerating. Now, a note, when F2 equals F1, that also means that I2 equals I1. What that means is literally there will be no net current in the circuit. There's theoretically, there's these two currents going in opposite directions, but if you stuck an ammeter in the circuit, the ammeter would read 0 because the net current is 0. When you have an apparatus like this, it's called a rail gun. And you can actually project a projectile, the bar, very fast with a high voltage and a low resistance. As a matter of fact, the military has worked on and has developed rail guns. This is a way to actually propel something using a battery and a magnetic field. So I just wanted to mention this. This is the third example, and it's just a difference from the second example, and it's a pretty cool one. So hope you enjoyed it. There's more to come.